Next up is buffers. This is similar to what you've been doing. The biggest difference is you now have some conjugate base when you first start the reaction. So whereas a weak acid you only had Ca, for a buffer solution you've got some of the weak acid and the conjugate base. Or in another case, some of the conjugate base and some of the conjugate acid. Now, because you have a starting material, that now changes things, and that puts Cb, the initial concentration of base, in the equilibrium equation. And so we can see a shortcut first of all. Let me go ahead and give you that equation. There is your shortcut. And this is analogous to what we will see in a minute is a very important equation known as the Henderson Hasselbalch equation. And that is common fare for most chemistry tests, especially standardized type tests. And there is your shortcut for the hydroxide concentration for a conjugate base. Now, the components here are the initial constant of your acid, the initial concentration of your base, and your Ka. So let's see how that might look in the form of a problem. Calculate the pH of a solution that is 0.1 molar in acetic acid. I'm already suspecting a weak acid. And 0.2 molar in sodium acetate. And here's what you need to realize. That is an acetate. That is the conjugate base of acetic acid. You have a conjugate acid-base pair. And so therefore you're going to have a buffer solution. So this alone would have been a what? It would have been a question, a salt question. If I ask you about 0.1 molar acetic acid, that would be what? A weak acid one. But you put both of them together, you have a buffer. By the way, the Ka for acetic acid is 1.5 times 10 to the minus fifth. How do you normally work that? Do a Rice equation. Notice you're starting with both of these. You use x to be your difference. You then set that equal to Ka, and then you write expression for Ka in terms of H plus, which this case is represented by x. You solve for x or H plus and come up with your answer. Or you can take the shortcut, which is once you recognize this as a buffer solution, you can just go straight here and plug it straight into this equation. Notice, if you go the long way, it's going to be the same thing, because once you solve for this one, you're going to have what? X is equal to Kc times 0.10 divided by 0.20. And that is exactly what you have here using the shortcut. So I would advise you to cut straight to the chase on a test. When you see it's a weak acid buffer system, go straight to your shortcut equation, and that will take you immediately to that. H plus, of course, goes to pH. Now, this is percent ionized. We've talked about those before, so you know how to do percent ionized. You've just calculated H plus. You know the original concentration of your acid. Just report your answer this way as opposed to H plus or pH. Next problem. Rather, next concept. Henderson Hasselbalch. Let me go ahead and show you that version because it is so popular in chemistry text. You know, for this equation right here, Ka is going to be represented by this. If I rearrange for H, I get this. And notice this looks just like our shortcut equation. Ka, concentration of acid, concentration of base. But what do we have? Henderson Hasselbalch immediately takes the minus log of each of those, and then the minus log of that of H plus is pH, minus log of Ka is pKa, and minus log of HA divided. It leaves it like that, but the final version normally, and this is tricky, normally puts the anion on top. Well, isn't that wrong? No, it's not wrong if you change this to a plus sign. And this is the version that the Henderson Hasselbalch normally takes. pH is equal to pKa plus log of the anion divided by the acid. So again, that's a variation of that. Sometimes I use this shortcut, and sometimes I use this, depending on what I'm trying to do. If you're going for pH, I don't bother with a conversion. I'll go straight with the Henderson Hasselbalch equation. Okay, so now let's look at a question to close this one out here in a second. Calculate the pH, okay, fine, of a solution that is created by adding 100 milliliters of acetic acid. Right now I've got a weak acid problem going, and 400 milliliters of sodium acetate. Oop. I see now I have what? A salt, an anion. I have the conjugate base of that. So I know that looking at that, immediately I know I have a buffer solution. I'm either going to use my shortcut equation, or I'm going to use the Henderson Hasselbalch equation, whichever gets me there quicker. Here's the trick in this, and why I chose this one to work. In this particular case, you have different amounts of these. This didn't tell you how much was in the same solution. This is pre-mixing. This is the concentration of this pre-mixed with the conjugate base, and this is the volume of this pre-mixed. What you really have to do in this case then is you can't really use concentration of acid. You've really got to use moles of that, because each of these is not in the same container, because you have different amounts of each. You have to switch to moles. Normally we do concentration because it doesn't matter what the volume is. Moles is proportional to volume if these are in the same container at the same time, but these are different. So now, just to remind you, what's moles? My trick of water, how do you calculate moles? It's MOL, right? MOL is equal to MOL. So here we have molarity times liters. In this case, I'm going to use milliliters because it's on top and bottom and it'll cancel out. And then I have molarity of the base times the milliliters. And so here we've got the correct notation here of moles. This accounts for the fact that there's 4 times more of this material than that material. You have to weight that appropriately. And so what I wind up with is a pH of 5.05. Does that make sense? Sure. You're going to have a buffer of a weak acid, so you think it's going to be somewhere between what the pH of the acid is and what the neutralization point is. Right. And just to show you that you could have gone the other way, I also worked this out using the Henderson Hasselbalch equation, where I plugged in the concentrations of A and the concentrations of HA. Here I went ahead and converted it to 500 mils each, corrected for it this way, and you wind up with exactly the same answer, or very close to it.